Imagine you have a piece of rope with mass per length of lambda hanging from 2 points, and you're trying to figure out what kind of curve this is. For solving this problem, I'm going to focus on these 2 points of the rope, which the first one is the lowest point of the rope, and the second one is just a random point on the right side. If I call the tension of the rope at this point T, the tension of the rope at this point T0, and the angle here theta, what I would have is that T times sine of theta is equal to M, which is the mass of this part of the rope, times G, which I can write as lambda times L, which L is the length of this part of the rope, times G, and T times cosine of theta is equal to T0. If I divide the left side of the first equation by the left side of the second equation, and if I do the same things with the right sides, what I would get is that tangent of theta is equal to lambda times G over T0 times L. And I can write tangent of theta as dy over dx at the point which is y prime, and this is equal to lambda times G over T0 times L. If I differentiate both sides with respect to x, what I would get is that y double prime is equal to lambda G over T0, which is a constant, times dl over dx. For a really small piece of rope which has a length of dl, I have that dl is equal to dx squared plus dy squared, and I can write that equation as y double prime is equal to lambda times G over T0 times the square root of dx squared plus dy squared over dx, which is same as lambda times G over T0 times square root of 1 plus y prime squared. And now I have this really beautiful differential equation, and I'm going to solve it. So for solving this equation, I'm going to introduce another variable, u, which is equal to y prime, and what I would get is that u prime, I can write y double prime as u prime, is equal to lambda G over T0. I'm going to call this constant a times square root of 1 plus u squared. Left side, I can write it as du over dx. With a little piece of algebra, what I would get is that du over square root of 1 plus u squared is a times dx. If I integrate both sides, I would get that a times x plus some integration constant, c0 I would call it, equals the integral of du over square root of 1 plus u squared. I'm going to do a substitution. I'm going to say that let u be equal to hyperbolic sine of some variable z. So du would be equal to cosine hyperbolic of z times dz. Excuse me. So this integral would change to hyperbolic cosine of z dz over square root of 1 plus hyperbolic sine of z squared. Which 1 plus hyperbolic sine of some variable z squared, which is same as hyperbolic cosine of that variable. So this is hyperbolic cosine of z over hyperbolic cosine of z times dz, which is the integral of dz, which is z, which is inverse hyperbolic sine of u. So what I have here is that a times x plus its integration constant c0 is equal to inverse hyperbolic sine of u, which is same as y prime. Now, let me clean up a little bit. What I have here is same as hyperbolic sine of a times x plus c0 is equal to y prime. If I take the antiderivative of both sides, what I would get is that y is equal to 1 over a times hyperbolic cosine of a times x plus c0 plus another integration constant. I would call it c1. And yeah, that's it. So the shape of the rope would be a hyperbolic cosine. I think it's really amazing. These two constants, c0 and c1, are easy to calculate. They only depend on the origin of coordinates. For example, if I put it here, I can easily calculate c0 and c1, but for calculating a, which is lambda times g over t0, or for calculating t0, for most of the part, if these 2 points are just random points, not at the same level, you'll need numerical solutions. Yeah, I hope you enjoyed this video, and see you later.